trying to work in a remote country without the benefit of instruments or medicines. To properly explore this country of the cold, Boyle lamented the lack of a vital tool, an accurate thermometer. It was not until the mid-17th century that glassblowers in Florence began to produce accurately calibrated thermometers. Now it became possible to measure degrees of hot and cold. Because rather than mercury, they used alcohol, which is much lighter, they made thermometers that were sometimes several meters long and were often wound into spirals. But there was still one major problem with all thermometers: the lack of a universally agreed temperature scale.
There are all kinds of different ways of trying to stick numbers to these degrees of hot and cold, and they, on the whole, didn't agree with each other at all. So one guy in Florence makes one kind of thermometer, another guy in London makes a different kind, and they just don't even have the same scale. And so there was a lot of problem in trying to standardize thermometers.
Imagine that you want to make a scale of temperature. What do you do? Well, the obvious thing to do, and this was well understood by instrument makers and experimenters in the 17th and 18th century, is to try and find something in nature which you know always has the same temperature and make that your fixed point. A better strategy even is to find two such phenomena in nature, and then you have a lower fixed point, say something rather cold, and an upper fixed point, something rather warm, and divide the degrees of temperature between into, say, 100 convenient bite-sized chunks. The problem, however, was to define a phenomenon whose temperature you guessed was fixed. So for the lower fixed point, you might choose the temperature of ice, just as it's melting. And then there's an almost indefinite range of possible candidates for your upper fixed point. Isaac Newton, for example, worked rather hard on constructing what he called a scale of heat. He, for example, defined the temperature which a human can only just tolerate if they plunge their hand into warm water. It could be the normal human underarm, the temperature of the human blood, the temperature of wax just as it's melting.
The first temperature scale to be widely adopted was devised by Daniel Fahrenheit, an accomplished instrument maker who made thermometers for doctors in Holland. He used a mixture of ice, water and salt for his 0 degrees, ice melting in water at 32 degrees, and for his upper fixed point, the temperature of the human body at 96 degrees, which is close to the modern value.
One of the things that Fahrenheit was able to achieve was to make thermometers quite small. And that he did by using mercury, as opposed to alcohol or air, which other people had used. And because mercury thermometers are compact, clearly, if you're trying to use it for clinical purposes, you don't want some big thing sticking out of the patient. So the fact that he could make them small and convenient, that seems to be what made Fahrenheit so famous and so influential.
It was a Swedish astronomer, Anders Celsius, who came up with the idea of dividing the scale into 100 divisions.
The original scale used by Celsius was upside down. So he had the boiling point of water as 0 and the freezing point as 100, with numbers just continuing to increase as we go below freezing. And this is another little mystery in the history of the thermometer that we just don't know for sure. What was he thinking when he labeled it this way? And it was the botanist Linnaeus who was then the president of the Swedish Academy, who after a few years said, well, we need to stop this nonsense, and inverted the scale to give us what we now call Celsius scale today.
A question nobody thought to ask when devising temperature scales was, how low can you go? Is there an absolute lower limit of temperature? The idea that there might be would become a turning point in the history of cold.
Now put the beaker of boiling.
The story begins with the French physicist Guillaume Amonton. He was doing experiments heating and cooling bodies of air to see how they expand and contract.
We're now going to put ice around our bulb and see what happens.
And he was noticing that, well, when you cool a body of air, the volume or the pressure would go down. And he speculated, well, what would happen if we just kept cooling it?
By plotting temperature against pressure, Amonton saw that as the temperature dropped, so did the pressure, and this gave him an extraordinary idea.
Amonton started to consider the possibility, what would happen if you projected this line back until the pressure was zero? And this was the first time in the course of history that people had actually considered the concept of an absolute zero of temperature. Zero pressure, zero temperature.
It was quite a revolutionary idea when you think about it, because you wouldn't just think that temperature has a limit of a lower bound or zero, because in the upper end it can go on forever, we think, until it's hotter and hotter and hotter. But somehow maybe there's a 0 point where this all begins. So you could actually give a calculation of where this 0 point would be. Amonton didn't do that calculation himself, but some other people did later on. And when you do it, you get a value that's actually not that far from the modern value of roughly minus 273 centigrade.
In one stroke, Amonton had realized that although temperatures might go on rising forever, they could only fall as far as this absolute point. For him, this was a theoretical limit, not a goal to attempt to reach. Before scientists could venture towards this 0 point, far beyond the coldest temperatures on Earth, they needed to resolve a fundamental question. By now, for most scientists, the penny had dropped that cold was simply the absence of heat. But what was actually happening as substances warmed or cooled was still hotly debated.
The argument of men like Amonton relied completely on the idea that heat is a form of motion, and that particles move more and more closely together as the substance in which they're in gets cooler and cooler.
Unfortunately, the science of cold was about to suffer a serious setback. The idea that cooling was caused by particles slowing down began to go out of fashion. At the end of the 18th century, a rival theory of heat and cold emerged that was tantalizingly appealing, but completely wrong. It was called the caloric theory, and its principal advocate was the great French chemist Antoine Lavoisier. Like most scientists of the time, Lavoisier was a rich aristocrat who funded his own research. He and his wife, Madame Lavoisier, who assisted with his experiments, even commissioned the celebrated painter David to paint their portrait. Lavoisier carried out experiments to support the erroneous idea that heat was a substance, a weightless fluid, that he called caloric.
He thought in the solid state of matter, molecules were just packed close in together. And when you added more and more caloric to this, the caloric would insinuate itself between these particles of matter and loosen them up. So the basic notion was that caloric was this fluid that was, as he put it, self-repulsive. It just tended to break things apart from each other. And that's his basic notion of heat. So cold is just the absence of caloric, or the relative lack of caloric.
Lavoisier even had an apparatus to measure caloric, which he called a calorimeter. He packed the outer compartment with ice. Inside, he conducted experiments that generated heat, sometimes from chemical reactions, sometimes from animals, to determine how much caloric was released. He collected the water from the melting ice and weighed it to calculate the amount of caloric generated from each source.
I think the most striking thing about Lavoisier is that he sees caloric as a substance which is exactly comparable with ordinary matter, to the point that he includes caloric in his list of the elements. It's very easy to talk about the quantity of heat and to think of it as a fluid, whereas to talk about the quantity of heat and to think of it as a vibration of the particles of matter, which was the other alternative, that's much more difficult conceptually.
It's a very hard model to refute, because if you can accept that there's a substance that doesn't have any weight, indeed for Lavoisier, heat, caloric, is an element. It's an element like oxygen or nitrogen. Oxygen gas is made of oxygen plus caloric. And if you take the caloric away, presumably the oxygen might liquefy. So it's a very hard model to shift because it explains so much, and indeed Lavoisier's chemistry was so otherwise extraordinarily successful. However, Lavoisier's story about caloric was soon undermined.
There was one man who was convinced Lavoisier was wrong and was determined to destroy the caloric theory. His name was Count Rumford. Count Rumford had a colourful past. He was born in America, spied for the British during the Revolution, and after being forced into exile, became an influential government minister in Bavaria. Among his varied responsibilities was the artillery works, and it was here in the 1790s that he began to think about how he might be able to disprove the caloric theory using cannon boring. Rumford had noticed that the friction from boring out a cannon barrel generated a lot of heat. He decided to carry out experiments to measure how much. He adapted the machine to produce even more heat by installing a blunt borer that had one end submerged in a jacket of water. As the cannon turned against the borer, the temperature of the water increased and eventually boiled. The longer he bored, the more heat was produced.
For Rumford, what this showed was that heat must be a form of motion, and heat is not a substance, because you could generate indefinitely large amounts of heat simply by turning the cannon.
Despite Count Rumford's best efforts, Lavoisier's caloric theory remained dominant until the end of the 18th century. His prestige as a scientist meant that few dared challenge his ideas. Sadly, this did not protect him from the revolutionary turmoil in France, which was about to interrupt his research. At the height of the Reign of Terror, Lavoisier was arrested and eventually guillotined.
The reason he was guillotined was not because of his science,